Hi, today I'm talking about computer security and cryptography. Basic security practices are increasingly important in software development. More and more of our life depends on technology. The cloud has been around for a while now, but it's the Internet of Things. It's getting on our fridges and other places. People depend on social networking for a lot of their interaction. There's e-voting, there's self-driving cars, and there's more and more data breaches. So security is important and it's a big topic. And cryptography, an important part of security, has a lot of deep mathematical theory behind it, which we're not going to go into depth on. But what we will do, and our goal, is to understand this overall domain at a level that's useful for regular development and with enough detail to give those of you who might want to learn more somewhere to look. And I'll be happy to share resources about that. To learn these topics, we're going to be taking a hands-on approach. We're going to be using a little bit of Python. We're going to be showing some JavaScript. And we're going to talk about modern security tools and practices, things like SSL and public key infrastructure and the web of trust. Overall, what we're going to be talking about is by the end of this, you should know a lot of the common security terms. You should know what a threat model is, why it's important, and you should know common security exploits and defenses, or as they're often called, mitigations, because often a defense doesn't prevent an attack completely. It just lessens the impact of it. We're going to know about symmetric versus asymmetric cryptography and some basics about how to use cryptography and best practices there. As I said earlier, public key infrastructure versus the web of trust, which are sort of two alternate ways to have a cryptography ecosystem. And we'll talk a little bit about the future of some security topics that are kind of exciting, things like blockchains and quantum cryptography. So with that, as I said, security is important, and this is just a somewhat humorous illustration of that. You may have heard a few years back when there was something called Heartbleed. Basically, what Heartbleed did is it allowed certain sorts of requests to web servers to return random dumps of their memory. And if you sent enough requests and you got enough random pieces of the memory, you could stitch together pretty much anything that was on that server. And this is obviously pretty bad, as they're joking. Well, the attack is limited to data stored in computer memory. Great. So paper is safe and clay tablets, right? On a somewhat more serious note, well, not that Heartbleed isn't serious, but data breaches in general keep happening, as I'm sure you're well aware, and I highly advise sort of giving a look at how they keep increasing and the costs of them keep increasing. Most recently, Equifax, you were quite possibly affected by that one. Yahoo, Anthem, which has health records, which are potentially sensitive. We'll talk a little bit about that, and many, many others. So, but I said earlier that we need to think about threat model. Security is a matter of context, and while it's important, it's all well and good to say it's important. If you are working as a software developer, you need to think, what is the context of security that I am facing, that my users are facing, that my application is facing? And that, in a nutshell, is threat models. Another humorous illustration of a crypto nerd who may or may not have a good threat model, thinking that their super powerful encryption will protect them from the NSA or whoever. And perhaps in reality, the encryption is not the weakest link of their particular security. Now, that said, most of us don't have to worry too much about this sort of situation here, hopefully. The first thing to think about with your threat model is, who are your adversaries? Basically, who do you trust and who do you not trust? If, for instance, well, not just if you're working as a modern software developer and you're pushing things to the cloud, you have to trust whatever cloud service or services you're using. So if you're using Amazon's cloud or Google's cloud, you are trusting them. Generally speaking, that's an okay thing to do for a lot of threat models. There might be some users or some people who are not comfortable doing that, and they have to pursue something else. But for most of us, Google is not an adversary. They are just a service we can use. But criminals might be an adversary, the sort of people who want to steal your identity. And there are other potential adversaries as well. Basically, who wants to hurt you and why? You also want to think about attack surface. This is, what is it that's exposed, what's most vulnerable to attack? In particular, what services, what live web services are you running? What ports do they have open? What are they doing? Versus what do you keep offline or behind a firewall locally? Potentially all those things can be attacked, but obviously the online services are the most vulnerable. And the other thing to think about is attack vector. How can these things be attacked? Basically, how do you take data in? How do you authenticate users? There's lots of different ways that things can happen to your system. And thinking about adversary, attack surface, and attack vector is how you build your threat model and make the decision about how you're going to approach security in your application. Just as an aside about sophisticated adversaries, as I said, we don't have to worry about the NSA as an adversary directly, or rather, if the NSA was deeply interested in any one of us, they could probably learn whatever they wanted. But there are some groups out there that do actually have to think about the NSA as an adversary. In this announcement in 2014, Google highlights the fact that they started encrypting everything that they were doing while moving the data internally from Google Data Center to Google Data Center. Previously, they hadn't done this because they figured it's going from us to us, and it's going over fiber that we own or lease. Encryption is just a waste of our resources. But it turns out if your opponent is, or your adversary that is somebody like the NSA, they can actually still potentially attack that, as the Snowden papers showed. And so that was one of the fallouts of that. Now, besides thinking about threat model, the other thing to think about are the common risks facing a user of software. And there's essentially three categories. There's confidentiality, integrity, and availability. Confidentiality you can think of as privacy. And this is making sure that your information is only shown to the parties that you want it to be shown to. A good example of this, as I mentioned earlier, with Anthem being hacked, presumably, or really any number of these, the people who had their data, had their health data in Anthem, really only wanted their doctors and other health personnel to know about it. They didn't want their data to get out to other people. So that violates the confidentiality of their data. And for health in particular, there are laws called HIPAA that are meant to ensure compliance and security standards to prevent things like this hack and to punish it when it occurs. Health is one of the somewhat more regulated industries in this regards. Regulation is still catching up in these other industries, and it will be interesting to see, for example, the fallout for Equifax, because right now we really don't know how much liability they'll face. But at the very least, it's a huge reputation hit, and I'm sure it's costing them at least a bit. After confidentiality, the next sort of risk facing the user of software is integrity. You can also think of this as authenticity. And what this means is having the data or information be shown and given to others or received from others in an unaltered fashion. This might sound a little bit not as big a deal as confidentiality at first, but it's actually a really big deal. Think if you're going to your bank website, you want it to be your bank website. You don't want it to be some website that somebody just put up, happens to look like your bank. You enter your password and you're happy, but the password actually just goes to this other person and not your bank. And then this other person can go to your bank and take your money and change your password. And that's not a good situation to be in. So the reason that's an integrity risk is the integrity of the data you received that you thought was your bank website. It was not there. It was not your bank website. That data was not authentic. It did not have integrity. Obviously, lots of potential for liability goes bad as well, just from a product or company perspective. And at the very least, a lot of support headaches. The third sort of risk facing a software user is availability. And availability is simple, but still pretty important. It's basically just having the service be up and work, respond, have the data overall, not just the integrity of the data, but just like not losing data. So examples of this being violated are whenever websites are supposedly hacked, which, really it's sort of the equivalent of graffiti almost. You're defacing a website with, say, a political statement. And this often looks bad for the website or brand being defaced. Also, denial of service attacks might just take it down. And also there are the sorts of exploits that actually just delete data. And this can cause quite a few headaches. And depending on what industry you're in and what sort of agreements you have with your customers, you might have some pretty significant financial losses in these cases as well. Even regular users are vulnerable to availability attacks. Something that's been on the rise in recent years is called ransomware, which basically takes over your computer, and we'll talk a little bit more about that sort of software later. But ransomware specifically takes your data, encrypts it so you can't get at it, and then tries to get you to pay them for it. So it's denying you the availability of your own, cat pictures or whatever it is you keep on your computer. And if you want to get at those, you have to pay money. So it's a form of extortion. And availability attacks are often forms of extortion. There are groups that go around saying, we're going to do an attack and take your website down unless you send us some Bitcoins, that kind of thing. So what are the sorts of attacks that violate confidentiality, integrity, and availability? Actually, this is not illustrated here, but one of these sorts of attacks, here we go, is called the man-in-the-middle attack. And the man-in-the-middle attack is when you have two people who want to communicate, say Alice and Bob, but you get somebody in between. This is Mallory. The other example is often Eve. But in any case, what this person in between is doing is they're intercepting the communications between Alice and Bob. And at the very least, they're listening in. That's called eavesdropping, and that's Eve. Eve is an eavesdropper, and that violates confidentiality. They can also potentially modify, be malicious, and actually change what Alice sends to Bob or what Bob sends to Alice. So Alice tells Bob, I'll meet you at the park at 2, and Mallory changes that to be, I'll meet you at the park at 3 or something. Bob doesn't show up. That violates integrity or authenticity of the data between Alice and Bob. So man-in-the-middle attacks are just a sort of classic and still very relevant attack to be aware of. And they're the sort of thing that we want to prevent. And proper application design and use of cryptography is basically how we do that. We will get to that shortly. Another sort of attack, as I alluded to earlier with availability, is denial of service. Specifically, though, what's common these days is called distributed denial of service. And distributed here means, first off, the way denial of service generally works is you flood something. You send a whole bunch of requests. Imagine if you're running your little server and all of a sudden 1 million different requests come in. Your server might just give up and crash. Now, if all of those million requests come from the same area, you're able to look at the IP addresses and you realize, okay, this is just like this one network that must have a lot of resources, but still, you can just blacklist that one network and then you'll probably be fine. But in a distributed denial of service, what happens is the attacker has control of what's called a botnet, which is just a group of compromised computers. It could be, the computers of a grandmother, or these days it could be the computer in the refrigerator. And these compromised computers all do what the controller of the botnet asks them to do, at least in the background, and they come from all over. Grandmothers and others around the world end up clicking malware and joining botnets. And so there isn't any particular pattern to where they are, to their IP addresses. And so you can't mitigate a distributed denial of service so easy. Really, the only thing you can do is fail with it. And you've probably heard of CDN, content distribution networks, and one of their main purposes is to help scale and mitigate the impact of DDoS attacks. And then another sort of attack, just in general, is malware and backdoors getting inserted into computers. That's how you end up joining a botnet in the first place. Pretty much everybody who uses a computer is a target for these to some degree. Everybody with an email account gets that spam email that they really shouldn't click. There are also high value targets. For instance, John Podesta of the Democratic campaign last year was a high value target. And when he fell for something and gave up his email password, that led to all the email being leaked for the Democratic campaign, headaches. You as a developer, you're actually probably at least a mid-value target. And the reason is because, first off, you probably have a few more computational resources than most users. You have access to some instances in the cloud and so forth. You might just have a few more computers. But the other aspect is since you make applications, you make code that goes to a lot of other people. And so if you can be compromised, and then they can use that compromise of you to further attack the users of your application, that's a big problem. And sort of later on, we'll get to development best practices. And a lot of them are actually just defending yourself. There's also things to think about for how you develop the application, of course. But in any case, so what are the sorts of attacks and exploits that implement the man-in-the-middle, denial of service, and malware, these sorts of things I was talking about? Well, one classic sort of exploit is injection. And injection is a whole class of exploits. Related to injection are buffer overflows. And I won't go into too much detail there, but remember when you were writing C code and you probably had more than a few headaches dealing with segmentation faults and freeing memory or not freeing memory or reading or writing memory in the wrong place. Well, it turns out that if your program allows the user to potentially put something, set a variable, like say their name, and make it so it grows outside of the space you assigned to it because you didn't put proper guards for that, they can put code in there that ends up in your C program and executing. These days, one of the main ways you might see this is whenever the latest video game console is rooted, it's often essentially a buffer overflow. For instance, I believe the Nintendo Wii U, you could install software that Nintendo didn't want you to install by getting a Zelda game and naming your horse something really, really long. And that just meant that, the variable name for that horse, or that horse's name, wasn't properly protected and led to a buffer overflow. As I said, though, code injection is big. Another sort of injection is SQL injection. And we don't need to go into too much detail about how it works, but this sort of comic illustrates a cute example where there's somebody whose name supposedly Robert, and then has this little close and then drop table students. And drop table basically means delete. So when the database admin of the school perhaps added this name, what actually happened is they executed drop table and lost all their data for their students. So a sort of availability attack, really. And as the comic jokes here, I hope you've learned to sanitize your input. We'll get to that more, but the short of it is you need to never blindly trust user input. Code injection is more general. There's SQL injection, but there's also what might look a little more familiar. There can be injection in HTML and JavaScript. There's a whole category of attacks called cross-site scripting, where basically by putting user modified code on the web page, they might be able to embed JavaScript from their other place and use it to grab cookies or authentication information, user data, or other things. I won't go into details of that right now. I just want to mention it as a class of attack. It's definitely a big deal and something to be aware of. And then more generally, there's also something called rootkits. Rootkits I mentioned because that's basically how you end up in a botnet or something like that on the first place. And this is what you get installed on your computer when you click that bad email or something like that. So what are some defenses against attacks? Well, this is just a general defense. It doesn't defend specifically against code injection, but setting good passwords is important. And really, you shouldn't think about them as passwords. You should think about them as passphrases. The reason is because password implies you should just sort of pick one word, right? And maybe an uncommon word, maybe you messed with it a little bit, but just one word. And it turns out that one word, even if you mess with it, isn't actually that hard for a computer to guess. If it can guess fast enough, it can figure that out. But if you pick something long, if you pick a passphrase, even if everything in the phrase is just a common word stuck together, it actually, just because of the length, is much harder to guess and is easier, hopefully, for you to remember. Now, this is not necessarily the gold standard. You can pick more words than this. You can still modify it a little bit, but you can certainly do a lot worse than just picking a random sequence of words. It's kind of important for it to be random. You don't want the passphrase to be something like your favorite quote, because somebody who knows you might guess that. Now, besides passphrases, obviously there's firewalls. Firewalls are not as cool as they are on TV, but they're still very important. Really, it just means having the same policy for what services you have open to the internet, what services and what ports you allow requests to come in on, and what you don't. There's sanitizing input. As I said, if it comes from a user, don't trust it. And in general, the code you run, if possible, if you're interacting with a database, you want it to be prepared statements or something that is guaranteed to be safe on the database, and that the user still will do things that will affect what you put in the database. Give you maybe a raw content field, but they shouldn't be giving you anything that can affect the actual interaction with the database. There's also isolation and permissions. So isolation and permissions basically means use containers, use the content security policy, which allows you to basically specify what resources are allowed to interact or be loaded on your web page. It's a way to mitigate cross-site scripting. Containers are like lightweight virtual machines that let you isolate different processes so they don't know about each other. These are both mitigation techniques in that they sort of prevent, maybe something still gets attacked, but it knows less, and therefore it can give less to the attacker. And then the big thing, really, encryption, which is what we're going to spend most of the rest of the time talking about. It's important to encrypt your data. Encryption can give, obviously, both confidentiality, but it can also give integrity, as we'll see. And it should be encrypted at rest. This means wherever it's saved in your database or as a file somewhere. And it should also be encrypted in transit, as we saw from Google. This means when it's going from point A to point B, from Alice to Bob. And there's this also practice called defense in depth, which basically means do all the above. It means a little more than that in some contexts, but the idea of defense in depth is you want to prevent attacks in as many ways and levels as you can, because they're going to happen, and when they happen, you want to limit their damage. There will be flaws in your defenses, but if you have another layer of defense below that, you might still be okay. So let's talk about cryptography. But first, let's talk about XOR. XOR, as you already learned when you learned a little bit about bitwise operations, means exclusive OR. And it's basically summarized as these pretty diagrams here, but I think it's best summarized with a simple truth table. You put in 2 zeros, you get a 0. You put in 2 ones, you get a 0. But you put in a 0, a 1, or a 1 or a 0, you get a 1. Exclusive OR. It is only true when it's strictly A or B. This is actually the way a lot of people mean OR when they just speak in common English and they say, oh, I want to do this or that. They usually don't mean this or that or both, which is what OR actually means logically. But still, that's how the convention is. For us, this sort of operation is called exclusive OR, or XOR. Now, what makes exclusive OR so important? Well, it powers what's called one-time pads. And I'm going to demonstrate with a few lines of Python here what a one-time pad is. But basically, the idea here behind cryptography in general, really, is that good cryptography comes down to good randomness. In principle, and this has actually also been done in practice for centuries, if two groups or people want to communicate securely with each other, and they both have a shared secret beforehand that they both know and they can both agree on. Say they both have the exact same copy of the exact same book, word for word. They can use that as data to XOR with their actual message. And so the person sending the message takes their message, XORs it with the first passage of the book, sends it to the other person receives it and knows, okay, it looks like gobbledygook, as you'll see. But if I XOR it again with the beginning of my book, I'll see what it actually is. And if you guarantee that only these two people know the key for the pad, the book that they're sharing, then this sort of encrypted communication is actually what's called perfectly secure. It has perfect information theoretic security. It cannot be cracked. It doesn't matter how many computers you have or whatnot. So it's not all done yet, as we'll get to, but I want to demonstrate it first anyway. So let's say the message you want to send is a very short message. And let's say the pad that both sides have agreed on is bar. I'm making the pad the same length as the message. And that basically has to be the case for a one-time pad. The pad has to be as long or longer, and then you just use that portion of it in the message that you're encrypting, and you can't reuse the pad. If you use the pad multiple times for multiple messages, then the man in the middle attack, Eve or Mallory, who are listening in, they can accumulate those and start actually figuring out what the pad is. But if it's just one message per pad or per portion of the pad, they can't. Now, what are we going to do with this? Well, we're going to make what I'm going to call the cipher, the encrypted bit, and it's going to be a XOR operation between the characters of the message and the pad. So just to explain what this is doing exactly, we are iterating over the pairs of characters. That's what zip is allowing us to do from the message and the pad. And before we XOR them, because these are characters in a string, we have to make them ordinal. We have to make them integers, basically. And then XOR can do its thing. Let's go ahead and do that. And now let's look at what we got out of that. We got 3 numbers. That doesn't look like much, really, but these 3 numbers correspond to the actual cipher text for the XOR of these 2 strings. And the way we can see that, we can build a ciphertext by converting these numbers back into characters, which I will do right now. So this is looping over the numbers and making them into characters and then just sticking them together in a string. Now, if we look at this, well, they look kind of funny, don't they? Well, that's okay. All this really means is that if you try to read these back as ASCII values, you'll find that they're outside the range of what you normally find, readable characters like the alphabet and the numbers and punctuation. They're these special characters that have escape sequences. But this is still a valid string. This is a string in quotes and all that. And you could print this, you could pass this on. Alice could give this to Bob. And if Alice does, and Eve gets it in between, Eve can't make any sense of this. Unless Eve has the pad, Eve doesn't know what this says. To decrypt it, what Bob would have to do is a very similar thing. Again, just XOR it, actually. But instead of zipping the message with the pad, they're zipping the ciphertext that we just made with the pad. And if they do this, like before with the cipher, they get this sequence of numbers. Well, that doesn't necessarily look that helpful, but actually these numbers correspond to the ASCII values for something a little bit more readable, as we will see. And indeed, what it gives us is the original message from the very beginning. So basically on line 7 here, our hypothetical Bob was able to take this ciphertext, which is just gobbledygook to anybody else, and use the secret pad, which nobody else has, we're just assuming that right now, and put it together to get back the original message that was intended. So that's just a very basic overview of using XOR, and there's a lot more to it, but that should be a good motivation overall, because actually the way crypto works in general is not that different from this, as you will see. So how does encryption then work more generally? Well, as I already said, it would be perfect if we could all just securely, secretly exchange arbitrarily long pads with each other, but we can't. So instead, what we do is we exchange shorter things, which we call keys. And these keys are used as seeds for random number generators. A random number generator takes a little bit of something that looks random, like a key, or it hopefully actually is random, but then it expands it into a lot more of pseudo-randomness that is supposed to still behave a lot like real randomness, but was generated by this algorithm, by this random number generator. And essentially, after that, after you expand the key using random number generation to be the size of whatever message you want to pass, it's not, strictly speaking, just XOR, but XOR is at the heart of a lot of encryption and is conceptually very similar to what happens at that point. The secret and the quality of the encryption comes down mostly to the quality of that randomness. And then it is a lot like a one-time pad that XORs and shuffles a bit and does some other things sometimes, but somehow just changes the content. And then the other person who has the same key can expand it the same way and use it to decrypt it. So let's talk a little bit about what are the basic crypto operations. So one thing that definitely you have possibly already encountered and should definitely be aware of is hash functions. Hash functions take some sort of input and output what's called a digest, which looks a lot like gobbledygook. And there's lots of reasons why this is important. We'll get to some of them shortly. But the idea is that this should be a one-way function. It should be very easy to take your input, well, somewhat easy at least, to take the input, run it through a hash and get this, but it should be essentially impossible for somebody getting this to go the other way and to figure out that, okay, actually this is Fox, right? This comes out a lot with integrity or authenticity. because you can use this to, if you calculate the hash as a developer, let's say you build a program and you want to give the installation file to somebody, you might calculate the hash of the installation file before you give it to them. And then you give them the installation file, but you also, perhaps through a separate channel, you say, by the way, the hash of it is whatever it is. And this lets them calculate the hash of the file they received to verify that it really is the program you gave them, and it isn't something else that could potentially throw a backdoor or malware on their system. And actually, pretty much all reputable package managers do something like this fairly automatically. We'll get to that a little bit later with best practices. More on hashes later, but what are the other sort of basic crypto functions? Well, there's essentially 4 of them: signing, encrypting, verifying, and decrypting. And not all applications use all of these. We'll start with something simple here. This lets you encrypt and decrypt messages. So what that means is that if you generate a key and then you have your secret message here, and then you also have to generate your nonce, and I'll describe what that means in a moment, and then you click encrypt, you get some ciphertext. And then if somebody else goes to the same website and paste in here pastes in the same stuff, so they paste the ciphertext that they got, and they also have to have the same key and the same nonce, and then they decrypt it, they get the secret message. Now, what's the difference between the key and the nonce? The key is supposed to always stay the same. The key is secret, and it's assumed that both parties have that key and have already managed to securely exchange it, or perhaps this is just the same party. This is you, and this is you again later, and you just know the same key. The nonce is here not to be secret. You can actually pass the nonce along with the ciphertext to the other person. So if we want to do another message, we should generate a new nonce. Nonces are supposed to only be used once. We keep the key, we encrypt, we get a different ciphertext, and now we pass that and we pass the nonce, and they get the next message. You change the nonce each time to basically make it harder for an attacker to track patterns and figure out what the secret key is. We'll get to more on that in a little bit. So what I just showed you is called symmetric cryptography. The symmetry is because both parties, or as I said, possibly just you over time, have the same secret key. But there's something called asymmetric or public key cryptography. And to share a little bit about how that works, I'm just going to play a little video excerpt that has an analogy regarding colors.
So how could 2 people who have never met agree on a secret shared key without letting Eve, who is always listening, also obtain a copy? In 1976, Whitfield Diffie and Martin Hellman devised an amazing trick to do this. First, let's explore how this trick is done using colors. How could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on 2 facts. 1, it's easy to mix 2 colors together to make a third color. And 2, given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock. Easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they agree publicly on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private colors. Now, Alice keeps her private color and sends her mixture to Bob, and Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrived at a shared secret color. Notice how Eve is unable to determine this exact color since she needs one of their private colors to do so. And that is the trick. Now, to do this with numbers, we
Won't go through the rest of this video now, but I encourage you to watch it. But if we go back to how this might work with something like this, and this website, by the way, I'll talk about more later, is an implementation of what's called NACL, native crypto, in JavaScript. And it's something that you have the opportunity to play with. But if we want to do this here, the idea again is that we want two parties to generate a shared secret and to do so in a way that the eavesdropper can't get at. And when you heard that mixing colors and how it's easy to go one way and hard to go the other, you might have thought, well, that sounds kind of like, you know, the hashing thing we learned about. And yes, there's definitely some similarities and connections there. I'm not going to have time to go into all the math for that though, but conceptually there's a lot of similarity. Now, what we do here is whenever you generate your secret key with an asymmetric crypto system, you get a public key as well. And the public key really is public. You are allowed to put this anywhere. You put it in your Twitter profile and say, this is me. That's probably a good thing to do. And let's say somebody else is doing the same thing here. So I have two tabs here. Unlike last time, I'm not going to paste the secret key across tabs. This person generated their secret key in secret, this person generated their secret key in secret, and neither of them ever share this with anybody. But they do share their public keys with each other. So Alice gives her public key here to Bob, and Bob gives his public key here to Alice. Now, Alice wants to send her message, so she comes up with her message, and remember, she's also going to generate a nonce. This is not secret. This is just more randomness to go into the encryption to make it harder to attack. She encrypts it, and she gets ciphertext and a nonce. She gives these things to Bob, so Bob has the ciphertext, and Bob has the nonce. And when he has these, he can decrypt and get the message back out. Now, this example that I'm showing you, you might notice earlier I said there's encrypt, sign, verify, and decrypt. But here there's just encrypt and decrypt. Well, that's because this is a simplified API that does both at once. Encrypting always signs and decrypting always verifies. All this means is that when Alice generates the ciphertext doesn't just say, meet me in the park at 2. This says, meet me in the park at 2, and I am Alice. I am the person who owns this public key. And then when Bob decrypts it, the result isn't just the plain text. He gets that, meet me in the park at 2, but he also gets it in this person's public key. And if you don't have the right public key here for them, you have some wrong public key and you try to decrypt, it's, well, actually, let's at least pick a valid public key. Let's say instead of CZ, it's AZ. For some reason, there's something off in the public key. And you try to decrypt, it actually won't decrypt because it'll say this is not verified to this key. So more about how public private key cryptography works. Now, you might then think that this solves it, but you still need to have everybody's public key. This is a little bit easier than knowing everybody's one-time pads. It's short, but you still need a way to know, okay, this is the public key of my bank and I trust it. And so when I go to their website and see it, I know that I'm really at their website. And to do that, we need some sort of public key infrastructure. So what is public key infrastructure? This is how, in practice, your operating system and your browser know what public keys to trust as being associated with certain entities, and thus what websites to trust because they have certificates that are signed by these public keys, and then you're able to say, okay, this really is mybank.com. The way they are organized is there are organizations called certificate authorities, and these are usually security or telecommunications or sometimes web hosting companies. And they're trusted to keep really secure keys, and then they use their secure keys to sign the keys that they give to other people. And then the browser and OS vendors, Google, Microsoft, whoever, put built into their operating system and their products the list of the certificate authorities to trust. And that way, when somebody goes to their website, they just know right away, yeah, it works. This is the real thing. The advantage here is usability. There's no end user setup. And assuming you trust your vendor, again, this is the threat model. If your threat model is, you don't trust Google or Microsoft or something, then that's much harder. But if you trust your vendor, this can actually have kind of decent security. But the disadvantage here is centralization. The sort of hierarchy of certificate authorities, and if any one of them, especially an important one, goes bad, a lot of damage could happen. And goes bad doesn't necessarily mean like decides to go bad. It could just be they get hacked, right? And that would be, they're a very high value target is what I'm saying. And there are ways to mitigate this. Google, for instance, tries to push patches really quickly to Chrome whenever there's a certificate authority that's compromised. But not every device is running up-to-date Chrome. The Internet of Things doesn't get patches very often, and this leads to devices that can be compromised and made to install malware and join botnets and lots of other problems like that. So what's the alternative then to public key infrastructure? Well, there's this alternative that's been around for a while called the Web of Trust. And this is basically an idealized model for tools like GPG, which is an open source version of PGP, pretty good privacy, which you've probably heard of. It's usually what crypto people point to as like, this is the encryption software that you can trust if you're really paranoid and you're trying to protect yourself from the NSA and all that. And in this case, you have users who generate and manage their own key pairs and then supposedly go to key signing parties, and they use their key to sign the key of their friends. They show each other their keys, and they attest to the fact that this key comes from this other person and vice versa. Just as an aside, I should give a little bit more detail on what signing is and how it works. Essentially, remember how I said there's the one-way, hard to reverse hash functions. And if you take the data that you want to sign and hash it, and then you encrypt the hash using your private key and attach it to the data as a certificate, the person who receives the digitally signed data, which is really just the data plus your encrypted version of the hash, they can take your public key and decrypt it, because again, the way asymmetric cryptography works is what you encrypt with your private key, they can generate a shared secret using the public key and decrypt it. They independently calculate using the same hash function their version of the hash of this data, and they see if the version that they get from your signature when they decrypt it equals it. And if it does, They know that both the data is the data you said it was, and you are who you say you are because you provided something that decrypted using that public key that they know to trust. So back to the web of trust, the idea is by having this signing and verification process, and now what you're signing, the data here is actually other people's public keys. You're saying, I believe that this, and it's a bit more, it's a whole statement that says this public key belongs to somebody, right? And if you sign the public keys of your friends, and they sign the public keys of their friends, and so forth, the idea is pretty soon everybody can trust each other because you trust your friend's keys. And so if you see your friend's keys used to sign somebody else's keys, you trust those person's keys, and so forth and so on. Trust here means that you believe those keys belong to the person who claims to own them. And you can think of, if you've heard of 6 Degrees of Kevin Bacon, which is the game where you name any actor and you try to figure out if this actor was in a movie with somebody who was in a movie with somebody who was in a movie with somebody, etc., who was in a movie with Kevin Bacon. And the idea is you can always get to Kevin Bacon within about 6 steps. You know, Kevin Bacon in enough movies, right? This all sounds great, and there are people who use this and enjoy it, but generally speaking, they have to really know what they're doing. They have to know how to set this up and manage this themselves, and they have to be the sort of person who goes to key signing parties, which are probably unusual. And basically, without proper setup, this can be arbitrarily disastrous. You know, if you forget your passphrase, that's it. You've lost your data. Nobody can help you. If the keys are outdated or insecure, or somebody signed something they shouldn't and you don't know to trust them, it can fall apart pretty quickly. But really the big problem is adoption. It's too complicated. Most people just won't do this. They want something to just work, kind of like the public key infrastructure. Now, is there a solution? Is there a way to sort of cross the usability security divide and give some decentralized security? Because again, the advantage of this over public key infrastructure is it's decentralized. You don't have to trust Verizon or Komodo or Symantec, and you don't have to trust that those companies won't get hacked. Well, there's an interesting project, a startup called Keybase, that tries to essentially make key management and key signing parties a little more modern and useful. I just want to call it out because I think it's pretty neat. Instead of going to a party, you just publish these sorts of proofs, these signing and verifications on your social media. The idea is they already know who you are on Facebook or Twitter, and they trust that that's who you really are, you know, because you post whatever you post, pictures and wherever you've been, and they know that that's you. And so if you post this proof, that verifies that you really hold that public key. And that's what key is. So what do you need to know about cryptography as a developer? That's really what this is about. We've talked an awful lot, and I really only scratched the surface on a bunch of things. So really, the first thing you need to know is how to pick the right protocols and tools and parameters. And this is complicated. A good start is this website I'll show here, called Cryptographic Right Answers. It's written by somebody named Colin Percival, who is well respected in the software security world. He wrote one of these things he's recommending, scrypt. Scrypt is a password hashing algorithm. There's that word again, hash. And I want to talk about password hashing in particular because it's definitely another developer best practice. You don't need to understand or read all of this, and some of this is a little dated. This is from some years ago, and there's conversation from the past months about, hey, what's more up to date? Is this still okay? What should we do? But basically, cryptography is always a race against time. There's always the possibility that some flaw will be found in an algorithm, or something like that. Up until somewhat recently, a hash algorithm named MD5 was very, very widely used. But these days, you really shouldn't use MD5, and according to Colin Percival, you shouldn't even use SHA-1. Both of these are vulnerable to attacks. And Colin even thinks SHA-256 might be broken soon, so maybe you should use something even more modern. And these are all just different ways of shuffling and trying to use crazy math to try to make that one-way function. But the point is when you need to do an application, do your homework and pick good tools. The Tweet Knackle that I highlighted earlier is a good, simple tool that makes a lot of good decisions for you. As I said, it combines encryption and signing and decrypting and verifying for you, so you don't mess that up and do those in the wrong way. And it makes good decisions about algorithms. And there's other software packages like that that I will provide as resources. Relatedly, NIST, which is a government organization, provides recommendations for how long you should make your keys. This is in particular for asymmetric cryptography, how big of a key you need for it to be secure for how long. This is just another resource and the sort of thing you should look at. But the overall message here of picking the right tools, don't roll your own crypto. It's really fun to learn about crypto, and it can be educational to sort of make your own version of a cryptographic algorithm as you see those details. But just like, you wouldn't want to implement, you wouldn't want to use your own implementation probably of a sorting algorithm. You want to implement it to learn, but then you want to use the sorting algorithm built into the programming language or whatever framework or system when you're actually using it. The same thing, even more so for crypto, because the established crypto code has been battle tested. It's been out there for years. A lot of smart people have looked at it a lot. And so you should definitely keep using it and not roll your own unless you really specialize and go in that area in detail. So what are some other best practices then besides doing your homework, using the good tools and using them properly? Use OAuth integrated logins. And specifically OAuth 2, you'll possibly just see it called OAuth these days, but OAuth is an open standard for authorization and logging in. And basically it allows you to provide the login framework, the user login, and rely on companies like Google, Facebook, Twitter, Amazon, Apple, whoever, to actually maintain user accounts and handle things like password resets and security issues, multi-factor authorization, which we'll get to. These companies have whole teams of security engineers on call, and you kind of get this for free, at least for the login step, which is an important step if you use it. For specific services or situations, you might not want to use login from these services, but when you can, it's a good idea. And a lot of users are sort of used to it too. For a lot of markets, they might even like it. They don't have to come up with another password. So what else should you do as a developer? Well, personal security is important. You need to keep your own secret safe. As I said, you're at least a mid-value target. So, use good, turn on encryption on your local system, use good passphrases, not just passwords, back things up and encrypt those backups, especially if you put them in places that you don't directly control, all those sorts of things. Another best practice, use SSL. Basically get a certificate that lets you get this nice little lock on your web page. And these days, there's really no excuse not to do it because it's free and it's easy. Let's Encrypt lets you do it automatically, and you can, they have packages that integrate with pretty much all major frameworks and languages, and they're trusted in browsers. So it's not some weird organization. The operating systems and browsers ship with Let's Encrypt certificate trust installed, and you can see all their sponsors. So use SSL certificates for all production systems. And note, production doesn't just mean whatever your end users use. Depending where you are, production could mean internal systems that are actually on the open internet, something that's accessible to other users of the company outside of the local corporate network. What other good standards for a developer? Use public-private key pairs to log into things. Hopefully, you've already sort of set up an SSH key pair for your GitHub and push and pull and authorize with GitHub from the command line using public-private key pairs. That's that asymmetric crypto thing I was talking about earlier. And it's good, it works, and it's much better than passphrases because a key is longer than any passphrase you're going to remember. What else? Multi-factor authentication. This is twofactorauth.org, and it lists all the various services that you can turn on or ask them to turn on multi-factor authentication. And there's really quite a bit of them. The gold standard of multi-factor authentication is thing you know, that would be your passphrase. Thing you have, that would be your phone that gets an SMS message, or sometimes a dedicated little fob that you plug into a computer like a USB thing. And thing you are, this is biometrics, your fingerprint or your face or your eyeball or whatever. There aren't really any common services that support all three. Most services support thing you know, your passphrase, and thing you have, your phone. And it's good to do that. Really security critical projects might support all three. And obviously there are some consumer companies, most notably Apple, that has some biometric options these days. But the point is, use this because even you, clever developer, might one day just accidentally type your passphrase in the wrong spot or click the wrong thing, the wrong link from the wrong web page. And the damage of that, of losing your passphrase, is greatly lessened if you have another factor of authentication. Relatedly, don't reuse the same passphrase for everything. Have a few very good passphrases and then use a password manager to maintain long random passwords for everything else. What else should you do? You should check signatures when installing software. If you remember this, as I said, data here might be something that you're using to install a package or a library or an actual application. And you should check the signature of it to make sure that it is in fact the application and not some rootkit that's going to compromise your computer. If you use a main reputable package manager like apt or brew or yum or whatever, you probably get this for free, but it's something to be aware of, especially if you're just downloading things from web pages. So that's enough best practices. There's definitely more to think about there. But as promised, I want to talk a little bit about the future of software security, because that can be pretty exciting too. You've probably heard of blockchains and cryptocurrency, and you might be wondering, all this talk about cryptography, okay, what's a cryptocurrency? Well, a cryptocurrency is built off the same cryptographic primitives. It makes heavy use of hash functions and those sorts of things. But the goal is a little different than standard, asymmetric cryptography. You're not just two people passing messages back and forth. Instead, you're trying to create a decentralized, global, and usually public transaction ledger that is just a list of things, of transactions, of events, a list of numbers and timestamps. And that this list is something that everybody knows, everybody agrees on, nobody can dispute or change it, but no one group owns it. It's not like the Bitcoin bank can come in and say, no, this is how it works. No one entity owns it like that. Now, why does this matter? Well, money, the entirety of finance, basically is just a list of transactions. It's this list of, Alice sent $10 to Bob on June 17th. And to decentralize that basically means we no longer have to trust and pay for banks to be these entities that manage this. And instead, it's just sort of out there and everybody uses it. And there's this enthusiasm and idealism that goes with this sort of picture. Whether or not it lives up to that, I'm not going to, the jury's still out, I think. But it's definitely an interesting and really cool technology. And it's not just money. There's lots of things you can represent as a ledger of transactions, even though that sounds dry. tickets to go to an event. You could replace Ticketmaster, right, with the right sort of blockchain. News stories, you could have sort of decentralized, verified timestamps of news feeds. Communication, even. Now, the public aspect of the ledger means you're probably going to want to encrypt personal communication you put on it, but it's still a possibility, and there's applications in that direction. And also newer cryptocurrencies, you may have heard of Ethereum. Essentially what they do, what Ethereum specifically does, is it has more sophisticated scripting faculties built into it than Bitcoin. And what this means is it's not just a ledger, but you can actually program logic into these things on the blockchain to create contracts that are enforced with conditional logic. So you can make these agreements between multiple people in a decentralized fashion and be guaranteed, like holding money in escrow, guaranteed that the agreement will be enforced, but without actually having to trust some third party, some escrow agency. It just happens because of the decentralization in the blockchain. You might be asking, okay, hash functions, but there must be something else. You've probably heard of proof of work. Most blockchains use something like that to provide an incentive for miners, what they're called, to actually run the code to make the crypto work and to make this thing trustworthy. I'm not going to go into any more detail than that, but it's a really cool topic overall. And with the contracts from Ethereum, there's this idea that we'll have these decentralized autonomous organizations, basically like companies, but without CEOs or executives at all. The first one of those basically collapsed due to a security flaw, due to a hack in its contracts. And we'll see if the future holds more success for that idea. The one other topic that I wanted to address for the future that you've probably also heard of is quantum cryptography. Very, very sci-fi sounding thing, but it's actually something to really think about. I'm not going to talk at all about quantum computation itself, but essentially, if and when quantum computing gets powerful enough and big enough to work at a large enough scale to do things to attack the sorts of sizes of cryptographic problems, then remember all those one-way functions that we were talking about, those hash functions? They're no longer necessarily so one-way. It's much more easy to reverse them with adequately powerful quantum computation. And because of, now it's not true for every hash function. And so research area is something called post-quantum cryptography, which is basically trying to figure out what hash functions and what cryptographic schemes will survive a post-quantum world and what won't. So generally, quantum cryptography is about this, is about the impact of quantum computation on regular cryptography. That's because even when quantum computing comes, most likely it'll be held by powerful organizations at first, and the rest of us will still be using our non-quantum computers, but we might still want to have working cryptography to do so. You could also, think about actual cryptography performed by quantum computers, and that's a topic that I won't even get into at all. So overall, thank you for listening. I hope this was interesting and not too overwhelming. We will be doing some exercises to reinforce a lot of these topics, and I'll be providing resources if you want to go into more detail on any one in particular. Thank you.